My name is Amin Soltanieh, and I'm a research associate in Bundeswehr University, Munich. This is a research, this research is a joint research with Professor Markus Siegle. The topic of this presentation and paper is about solving systems of bilinear equations for transition rate reconstruction. So first of all, the outline of this presentation, at first I will talk briefly about the topics that we need, and I will talk about them in this presentation. Then I will talk about the background and the previous papers related to the bilinear system of equations. In the next section, I will talk about the special cases leading to complete systems of bilinear equations, and I will explain what is complete bilinear system of equations. In the next part, I will introduce a simple but relatively useful iterative algorithm to solve bilinear system of equations. And finally, there's a case study which is a tandem queuing network, and I will show the comparison for the run times of different algorithms. First of all, what is model checking? I'm sure most of you are familiar with it, but assume that we have a system and we have created a model of this system, and we need to verify some properties against this model. So if a model satisfies a certain property phi or not. What are these properties? We can classify them as safety, liveness, fairness, and etc. For example, if our model eventually leads to a deadlock or not. What is model repair? Assume that our model doesn't satisfy a certain property, doesn't satisfy property phi. Sometimes it is possible that we modify the system. Sometimes it is possible to modify the model such that the repaired model, the modified model, satisfies this property phi. There are different model repair algorithms proposed in different papers. So how can we perform model repair? Assume that we have a compositional Markov system, Markov model, and it is a synchronization of two components, M1 and M2, and they're synchronizing over some action sets, sigma S, for example. And this system, we assume initially that this system doesn't satisfy CLS, for example, property and until formula. In 2016, Soltanieh, he proposed a model repair algorithm based on rate reduction in the flat model, in the combined model of the system. So at the right-hand side, we have the system, the combined model of the system, and we assume that the model repair algorithm proposes to modify some of the rates of this combined model system by some modification factors. For example, we need to multiply the rates of R1 and R2 with factors F1 and F2. Now the question is it possible to reconstruct the rates of this system using this model repair information or not? Can we reconstruct the rates? So using a motivating example, I will explain more about this issue. We assume that we have two components, M1 and M2, and they are synchronizing with each other over action A. And in this system, we want to multiply the rates of all C transitions in the combined model by a factor F. So totally we have two C transitions in this combined model, and we want to multiply them by a factor F. In this case, it is relatively easy. So the only C transitions in this system exist in M2, this C transition. And if I multiply the rate of this C transition by factor F, then I can exactly have this combined model. So as you see here, if we multiply this rate by factor F, we can actually reconstruct the rates of this system. And we call it local repair because by just changing some transition rates in only one of the components, we can reconstruct the rates of the system. Now assume consider the same example, which is exactly the same example as the previous slide, but now we want to change the rates of these C transitions by different factors. So I need to multiply this transition rates by factor F1 and this one by factor F2. And F1 and F2, they are not equal with each other. In this case, we can't reconstruct the rates same as the previous slide. This is not as straightforward as the previous one. So if I multiply, so as I said, the only C transition exists in M2, and if I change this, the rate of this C transition, it will affect both of the C transitions in the combined model. But we can provide an alternative solution to reconstruct the rate. Assume that action C is added to the synchronizing set. In this case, the C transition in M2 must synchronize with something in M1. In order to realize these C transitions in the combined model, I need to add 2 self loops in states of M1. So in this case, to realize the C transition, this C transition in the combined model, the C transition in M2 synchronizes with this self loop, with the first self loop, and for the next C transition, it will synchronize with the other self loop. Now, every C transition, every self loop, and also the other C transition has a unknown variable for the rate of these transitions, and we need to calculate these rates. In order to formally calculate these rates, we can introduce a bilinear system of equations. So for every C transition in the combined model, we can write an equation and form the system of bilinear equations. And in this simple example, this bilinear system of equation has a solution, and we can easily obtain the solution. So this is one possible solution for this system. But of course, in general, the system of equations may have no solutions. And it is important to solve such systems of equations efficiently. So in case of a state space explosion, we may have thousands of states or transitions, and we need to solve a huge system of bilinear equations. And we will focus and we will address this issue in the rest of this presentation. So let's have a look at the background of the bilinear equation and the previous papers. So in general, a bilinear equation is in this form. So we have totally L bilinear equations in this system of equations, and it includes two disjoint vectors of variables. So the first one is X, and X includes n variable, and the other one is Y, and it includes m variables. Matrix AI is an n times m matrix, and it is a coefficient matrix. For example, this is an example of a bilinear equation, and it can include several bilinear terms. What is the complete bilinear system of equations? If the number of equations in the system of bilinear equations equals with the product of the number of x and y variables, so if it is equal with the product of n and m, then we call it complete, and we will see that it has some interesting features. So in 2009, Johnson and Link, they provided a solution theory for this complete bilinear systems. We can obtain the solution, and we can check the consistency of the system of equations using this formula. What is VEC? VEC is the vectorization operator, and it means that we take a matrix and we put all the columns of this matrix on top of each other, and we start from the first column. And matrix A, it is the matrix with the columns vectorized AI. How can we check the consistency of the system of equations using this formula? We should have a look at the rank of matrix G. If the rank of matrix G equals 1, then this system of equations is consistent. It has a solution. But we have a special case. In our special case, we have a simpler case. It is so we have only one bilinear term in every equation. Remember the motivating example in the previous slides. So we have just one bilinear term. Comparing with the general case, we have a simpler case. In this special case, matrix A, so you see matrix A here, it becomes an identity matrix. And so actually we can sort out the equation such that the matrix A becomes an identity matrix always. And if A is identity here, identity matrix here, so then the vector of G equals with D. So it will equal, so we can obtain G using only the right-hand side of the equations. So now in this section, we will talk about some special cases that always leads to complete system of equations. First of all, we need to define the system. The system is a Markovian compositional system, and so M1 and M2, they are two components. They are synchronizing with each other over synchronizing set sigma S. Assume that C is an action in this system, and in M1 we have some states that action C is enabled. So for example, A1, A2 until AP, they are the states that action C is enabled. And in A1, for example, we can have more than one outgoing C transition. So here, for example, we have K1 outgoing C transitions in A1. And similarly, it is symmetric in M2. What is EN1? So we call all the states that action C is enabled in M1 as EN1 stands for enabled, and same for M2. Also, there are some states starting AP1 until APQ that action C is not enabled, and we call them NE1, and it means it stands for not enabled. So this is the system definition that we have. Now we can state lemma 1 for synchronizing action. So we have the same system. We have the system that we described in the previous slide, but now we assume that action C is a synchronizing action. Now we can define all the C transitions of the combined model. So I just go quickly to the previous slide. Here you see, for example, from state A1, we have a C transition, and from E1, we have also a C transition in M2. If C is a synchronizing action, then these two C transitions, they will synchronize with each other. And in the combined model, we will have a state A1, B1 to A11, B11. So this is exactly what we see here. At the left-hand side, it shows all the C transitions in the combined model. And for every C transition, we can write an equation. And totally, we have M times N equations. So starting from D1 until dm times N. And what is M and N? M and N are the number of C transitions, or actually the variables in this system of equations in M1 and in M2. And as you see, the total number of equations is M times N. So actually, the total number of equations is the product of the number of variables in M1 and in M2. And that's why this system of equations is complete. So we can show it with this condition. Actually, if all these states in the combined model are reachable, A1, B1 until APBR. If they are all reachable, then we can have all these equations available. So we can show this with this statement here. All the states that action C is enabled in the first one and action C is enabled in the next in M2. They must all be reachable. In this case, if the system of equations is complete, then we don't have to solve the system of equations. We can verify the consistency of this system of equations by checking these conditions. They are very simple conditions over d1, d2 until dm times n, and by checking them, we can verify if the system of equations has a solution or not. So this was for synchronizing action. Now we talk about non-synchronizing action. We consider exactly the same system, M1 and M2 synchronizing with each other over some actions, and now we assume that C is not a synchronizing action. First of all, so remember from the motivating example that I explained in the first slides, sometimes it is possible that we add action C to the synchronizing set with some self loops, and we can reconstruct the system. So, but it is not always possible. Sometimes it is dangerous. Sometimes it creates some spurious or wrong transitions, and I will explain what are these wrong or spurious transitions. Assume that M1 and M2, they are synchronizing with each other. Action C is not synchronizing. So in M1 we have a state A1, and it is there's outgoing C transition, and it is same in M2 in the state B1. And this is the combined model of this combined model state of this system. And as you see, there are two outgoing C transitions because one of them M1 is moving, and in the other one M2 is moving. Now, if I make this if I make action C synchronizing, if I add it to the synchronizing set, then these two C transitions must synchronize with each other in a state A1, B1. But in this case, we will have a new transition, an extra transition, which is a wrong transition. We are trying to reconstruct the rates of the system. Somehow, we don't want to add or remove any state or transition from the original system. We want to maintain and preserve the original combined model of the system. But actually here with the spurious transition, actually we are adding some wrong transition to the system. So we should avoid such cases. How can we avoid it? We should make sure that states like A1, B1, they are all unreachable. So we can show it here, EN1 and EN2. So that states that action C is enabled in the first one and it is enabled in the second component, it must be unreachable. Okay, now we can state lemma 2 for non-synchronizing action. First of all, as I said, we should make sure about the spurious transitions. Then we can add action C to the synchronizing set, and we should add some self loops in the system in M1 and in M2. But where should we add the self loops? Consider this system M1 and M2 synchronizing with each other. In M1, in state A1, action C is enabled, and in M2, in B2, it is enabled. But in A2 and B1, there is no outgoing C transition. Now, if states A1, B1 in the combined model is reachable, then there exists only one C transition in the combined model in the state A1, B1. And similarly, there's only one C transition in A2, B2. And remember, state A1, B2 must be unreachable because of a spurious transition. Now, make action C synchronizing, then the C transition in M1, in state A1, must synchronize with something in B1 to realize the C transition in this combined model. And therefore, in B1 and similarly in A2, we need to have a self loop. And in this case, we have proved that the resultant system of equations, it always includes two complete bilinear systems of equations. And why we have two complete bilinear systems? Because one system of equations represent M1 is moving, and the other one is for M2 is moving. And in this case, if we want to have all the equations, I mean, to have a complete bilinear system, in that case, the states like A1, B1 and A2, B2, they must be all reachable states. So in order to show that, we use this expression. So this is a condition. And if this condition is satisfied, it means that all states like A1, B1 are reachable in the combined model. So the resultant system of equation is complete.
So you have 9 minutes left, including question and answers.
Thank you. Now, we represent an iterative algorithm. So far, we talked about complete bilinear system of equations. Now we introduce an iterative algorithm that we can use to solve even incomplete system of bilinear equation. It is relatively simple, but very effective. Assume that we have such a system of bilinear equations, and we start with the first equation, and we take one of the variables freely, for example x1, and we calculate the other variable y1. In the next equation, x1 is already calculated, so we calculate y2. In the next equation, y1 is already calculated, and we calculate x2. In the next equation, x2 and y2, both of them are calculated in the previous equations. So we consider this equation, and if it holds, then we can continue with the other equations. Otherwise, if it doesn't hold, then it means then we can stop the algorithm, and it means that this system of equations is not consistent. And if we have an equation like this, that x3 and y4 are not calculated in the previous equations, then we skip this equation and save it for the next iteration, because maybe later we find an equation that one of these variables can be calculated. So we save it for the next iterations. And similarly, we can continue until all the equations are considered and all the variables are calculated. We have an example here. It's a case study, tandem queuing network. Quickly, I explain this system. So there are two queuing systems. They are sequentially connected with each other, and the arrival, one of them is mcox21 queue, and the other one is an mm1 queue. The arrival rate is lambda, and the first queue provides service with probability A1 in two phases with rates mu1 and mu2, and with probability 1 minus A1 only with rate mu1, only in one phase, and then the MM1 queue. In this system, we can define the system like this. They're synchronizing with each other over action route. What is action route? It means that a job. It means that the job leaves the system, leaves the first queue, and enters the next queue. And it must take place at the same time in both of the queue. That's why it is in the synchronizing set here. C is the capacity of each queue, and this is the CTMC of the first queue, and this one is the CTMC of the MM1 queue, And the red transitions are actually the root transitions highlighted here. Totally, we have 2 times C root transition in the first one, in the first queue, and we have C root transition in the second queue. And as you see, we have in the combined model, we have 2 times C square root transitions, and which is the product of C and 2 times C, and that's why this system of equations, the resultant system of equations, is complete. And since it is complete, we can use lemma 1, the lemma that I explained in the previous slides, for action root. And this is the model statistics of this system for different values of C. So we want to compare the runtime of the solving of the system of bilinear equations for different values of C, starting from 200 to 500. This one shows the number of states in the system, and then the number of the total number of transitions in this system. And the last line it is important, it shows the number of root transitions in the combined model. And actually, it shows the size of the bilinear system of equations that we want to solve. It starts from 80,000 until 500,000 equations. And this is the runtime comparison, and this is the result for 3 different methods. One of them is lemma 1 that I explained to you. The other one is the iterative algorithm, and finally it is Gurobi. Gurobi is the commercial solver that we have used to solve the system of equations. And as you see, the lemma 1 has a better performance comparing with the other methods, and it was highly expected because lemma 1 actually just checks some simple conditions, and that's why it is quicker. So in conclusion, we have studied 2-component compositional model. It is a Markovian compositional systems, and the resultant bilinear system of equations for rate reconstruction problem. And we have identified some special class of systems that we can check the consistency by checking just some simple conditions. We have also introduced an iterative algorithm to solve incomplete system of bilinear equations, and the runtime comparison is studied in a case study, and we show that using the lemma 1, it is like 40% quicker than a Gurobi solver, which is a commercial solver. For future studies, actually, we are working on the systems with more than 2 components. It is almost ready, and we are finalizing to publish. Thank you so much for your attention.